we're going to talk about indeterminate forms and Hopitals rule. So an indeterminate form is when we're looking at the limit, if I get 0 over 0, infinity over infinity, infinity times 0, or infinity minus infinity. If we're in one of these forms, a lot of times we can do some manipulation and use Hopitals rule to find that limit. So Hopitals rule is suppose that f of a and g of a equals 0, and that f and g are differentiable on an open interval I containing a, and that g prime, so the derivative of g, does not equal 0 on I, if f of a, if x does not equal a. So we're looking at this limit. So this is a limit where f of x over g of x, and when we plug that in, here I have 0 over 0. What I can do is now take the derivative of just the top and the bottom. So this is not the quotient rule. This is the nice piece. We're going to take the derivative of the numerator and then put that over the derivative of the denominator. So Hopitals rule says, hey, I can take the derivative of this and find f prime over g prime. So our first example here is, let's say I have the limit as x goes to 0 of x minus sine x over x cubed. So when we're dealing with limits, the first thing we wanted to do is check to see if we can plug it in. So if I plug it in, I get 0 minus 0, which is 0, over 0 cubed, which is 0. So I have 0 over 0. Okay, that's okay. It just means that we have this indeterminate form. What we're gonna do is take the derivative. So I'm gonna take the derivative of the top. The derivative of x is 1. So I have 1 minus cosine x over 3x squared. Okay. All right. So now if I plug in 0, okay, I plug in 0, I get 0 minus 0, which is, 1 minus 1, which is 0. I have 3 times 0, which is 0. Okay, so I can take the derivative again. So now I have minus positive sine x, because the derivative of cosine is negative sine, over 6x. I plug in 0, I get 0 over 0. Okay, still indeterminate, so I'm going to take the derivative again. So the limit as x goes to 0, derivative of sine is cosine x over 6. Now I plug in 0, cosine of 0 is 1. So this is 1/6. So the limit as x approaches 0 of x minus sine x over x cubed is 1/6. So we're going to take that derivative, and we can do it multiple times. So here's our next one. So we're now going to find, if I plug in 0, I'm going to see if I get an indeterminate form and go from there. So cosine of 0 is 1. So I have 1 minus 1, which is 0. So the top is 0. 0 plus 0 squared is 0, so I have 0 over 0. I have an indeterminate form. So now I'm going to take the derivative. Okay. So now I have x goes to 0, so I'm going to take the derivative here. Derivative of 1 is 0. Derivative of negative cosine is sine. And now I have 1 plus 2x. I plug in 0, I get 0 over 1 plus 0, which is 0 over 1, which is 0. I am done because I'm not 0 over 0, but my limit is 0. Okay? So the next one is a little bit harder. So this is going to be that infinity over infinity. So I have the limit as x approaches pi halves of secant over 1 plus tangent. Well, if I plug in pi halves to secant, you can look at your radian conversion chart. I get infinity over infinity. It's probably typically infinity plus 1. So what I'm going to do is I'm going to take the derivative. So I take the derivative of secant. I get secant tangent. I take the derivative of 1 plus tangent. Derivative of 1 is 0. Derivative of tangent is secant squared. And now I need to do a little simplifying. So I'm going to cancel out my secants here. So this secant and one of the secants here cancels out, leaving me with the limit as x goes to pi halves of tangent over secant. I'm going to substitute in what tangent is and what secant is. So I have sine over x over 1 over cosine. Well, these cosines are going to cancel out, leaving me with the limit as x approaches pi halves of sine of x equals, and then I'm going to plug in pi halves. Sine of pi halves is 1, so the limit of this is 1. We had to take our derivative. Now we're going to have this idea of what happens when we're out at our extreme, our end value here, our end behavior. So what happens when we're going towards infinity? So if I look here, this gives me infinity times 1 over infinity, which we understand is 0. So sine of 0 is 0. So I have infinity times 0. So what I'm going to do is I am going to let h represent this piece in here, because what I'm trying to do is get this to be a fraction. Okay, so I'm trying to get it to be something over something, so that way I can take the derivative and use L'Hopital's rule. So what I'm going to do is I'm going to let h equal x over 1. Okay, so remember x is going to infinity. So this value right here, that is going to force h to go to 0. And we're going to say 0 positive, because remember this is a positive infinity, so we're on the positive side of 0. Okay, that's the only reason we're going to use that 0 plus. So if h is equal to 1 over x, x is equal to 1 over h. Okay, so we're just solving this equation right here for x. And now we're going to substitute in. So 1 over x is h, so I'm going to substitute in here. X is 1 over h. So I end up with the limit as h goes to 0 plus, because remember we changed our limit here, of 1 over h sine of h. Okay, I'm going to convert that to be this form, the limit as h approaches 0 positive of sine h over h. Can I plug in 0? Well, if I plug in 0, I get sine of 0, which is 0. This is 0, so I have 0 over 0. So now I need to take my derivative. So I take my derivative. The derivative of sine is cosine. Derivative of h is 1. So now I have the limit of h approaches 0 of cosine h over 1. And now I try to plug in 0. So I plug in 0 to cosine. Cosine of 0 is 1. So I end up with 1 over 1, which is 1. So L'Hopital's rule allows us to use those limit properties if I have one of these indeterminate forms. Okay. Sometimes we do have to manipulate it. So this was infinity times 0. We can't just go right here and take the derivative. We have to get it into this form for L'Hopital's rule to work. So we're going to have to do some manipulation on that. Okay. But L'Hopital's rule is nice because it allows us to just take the derivative of the top, the derivative of the bottom. If I still have 0 over 0, take the derivative again, and continue to do that. At some point, you'll either see, well, it's just bouncing back and forth. I'm not going to end up being able to simplify this at all. All right, so that's L'Hopital's rule.